Hello viewers, welcome back to the course on scientific computing using MATLAB. So, in the last lecture we have discussed about a problem and we applied the Newton forward and backward formula for that. Today we will go further and we will try to find that what will happen if the values of the x lies in between the finite difference table. So, today we will start with the Stirling formula. Stirling formula. So, the Stirling formula, I am going to give you the direct formula that how this formula look like. So, this is I want to find the value of x is equal to x naught plus ph. So, in that case I am giving you the value x naught and from here my p will be x minus x naught by h. So, this formula is applicable when the value of p is lying between minus 1 by 4 to 1 by 4. So, this is the value of the p, only then we can apply this formula. And we also know that the shift operator, I want to find the relation between E, that my delta can be written as E half minus E minus half. So, this is we already know. Now, I give you the direct that what is the Stirling formula. So, Stirling formula is I want to find Yp. So, that Yp is equal to, I can write Ep, that is Y naught. So, this is equal to Y naught plus P, and then I am taking del Y minus half plus del Y plus half by 2. So, I am taking the mean of these two values. Then p square by 2 factorial, this is delta square y naught plus, then I will write p plus 1 p minus 1 by 3 factorial, and then I am taking the average of half plus by 2. So, I am taking the average of this value same as this one, only difference is that this is the first order difference, this is the third order difference, and then plus. So, this will be equal to p square minus 1 by 4 factorial 4th y naught and so on. So, this is the Stirling formula for approximating a value that is lying in between the difference table. So, let us do one example and it will be more clear. So, let us take one example. I know the value. So, suppose I start with the value. So, this value of x is given to me, that is 1, 1.2, 1.4, 1.6, 1.8 and 2.0. The value of y is given to me. So, that is 2.7183, it is 3.3201, it is 4.0552, 4.9530, 6.0496 and 7.3891. So, this value is given to me. Now, I will take the difference table. So, I will write the first difference. So, again this is the 6 values. So, this is 0.6018, 0.7351, 0.8978, 1.0966, 1.3395. Then I take the second difference. So, second difference will be 0 0.133, 0.1627, 0.1988, 0.2429. Now we will apply the third difference. So third difference will be 0 point, so it is 0.0361, 0.0441. So it is the third difference. Then we apply the fourth difference. So fourth difference will be 0.0067 and 0.0080, and the fifth difference, the last value will be the constant value, and this is 0.0020, so it will be 13. So this is the last value. So this is my difference table. Now the question is that find y at x is equal to 1.44. So this value I want to approximate using the finite difference operator. Now from here it is clear that 1.44 lies here. It means if I need to find these values, then I will choose this value as x naught. So this will be x naught, this will be x minus 1, this will be x minus 2, x1, x2, x3. Now this, if it is x naught, this will be y naught. So this y naught I will take. The next is I will take average of these two values. Then I will, second difference, central difference will be this one. Then I will choose this average of these two value, then I will go here, and that is it. So using this Stirling formula, I should be able to find the value of x, the value of the y at x is equal to 1.44. The only condition is that my p should lies between minus 0.25 to 0.25. So let us see this one. So solution, my p will be x minus x naught by h. So my h in this case is 0.2. So this is 0.2, it is given to me. So x is my 1.44 minus x naught is, I am choosing 1.40 divided by 0.2. So this value is 0.04 divided by 0.2. So it is 0.4 by 2. So value will be 0.2. My p should lies minus 2.5 to 2.5. So it is satisfying here, so I can apply this one. Somebody can choose this as x naught. So in that case, if I choose this x naught, then the value of p will be negative. So everything depends upon that which value we are using. So in this case, I will use this value, so that's, this value is also okay. Now I will apply this Stirling formula to approximate the value here. So using Stirling's formula, the value of yp, so this will be equal to, so I will give these values. So I will take the value that is 4.0552 plus, so this value I am choosing first value, then the average of these two values, the next values. So plus p the p is 0.2 multiply by this 0.7351. So, I will write 0.7351 plus 0.8978 divided by 2. So, this is the average value I have taken. The next value will be p square by 2 factorial. So, it will be p square by 2 factorial and then this value will be equal to multiply by 0.1627. Then the next value will be again p plus 1 p minus 1 by 3 factorial. So, p plus 1 p minus 1 by 3 factorial and the average of these next two values. So, it is the average the next two value will be 0.0294 plus 0.0361 by 2 and then the last one will be the p square. So, 0.2 square 0.2 square minus 1 by 4 factorial into the last value that is 0.0067. So, I will stop here and then I will calculate all these values. So, if I do the calculations and my calculation is correct, then its value should be 4.2207. So, this is the value of y at x is equal to 1.44. So, this is the approximate value and from here I can see that this value 4.2207 is lying here. So, this value seems correct and from here I can see that this function is an increasing function also. So, based on this one I can say that this is my answer. So, yeah, now we have applied the Newton forward, backward and central. So, this is all about that whenever we have the data which is equally spaced, then we using these methods we can apply, we can find we can approximate the value of x based on that where this lies in the finite difference table. Now, this is about the equispace. So, let us do what will happen when the nodal points like x0, x1, x2 up to xn are not equispaced. So, in this case I will say that, so nodal point is, these points are also called mesh points. Somewhere it is also, sometimes it is also called the mesh points. So, what will happen when these are not equispaced? Like I have the data. So, my data is given to me, one value is here, another value is here, another value is here, then another value is here, this value, this value, this value, this value. So, in this case it is not equispaced, then I cannot apply Newton forward, backward or central difference as we have discussed. So, in this case we have to develop some other methods to approximate or to find the interpolating polynomial. Okay. So, let us do this one. Now, so first of all I will try to find that how we can find the any general interpolating polynomial. So, let us discuss that. Interpolating polynomial in general. So, suppose we have points, the nodal points x0, x1, x2 up to xn, n plus 1 points, not necessarily equispaced. So, this is not necessarily equispaced. Also, all xi are distinct. It means I can write this x naught less than x1 less than x2 less than xn. So, all are distinct. Now, the question is that I know that if this is the n plus 1 points, then we can approximate a nth degree interpolating polynomial passing through all these points. So, we want to find, we would like to find Px, the interpolating polynomial of degree less than equal to n. So, my Px can be written as a0 plus a1x plus a2x square up to an xn. So, this is I call it the equation number 1. Degree this, so that this satisfying, so it is satisfying the condition that my Pxi is equal to my fxi, the value of the function whatever is given to us, that is equal to Vi for all I between 0, 1, 2 up to n. So, that is condition there, that is passing through all these points. So, like this one, so some point is given to me, one point is given this, that. So, I am starting with this polynomial, like this one I am going. So, this is my Px, and this value whatever the points are given to me, this is the points. And it is satisfying this condition that it is passing through all these points. Now, I need to find what is my polynomial. So, we need to find Px, and that is the coefficients a0, a1, a2 up to an. So, to find the value of Px means I should know the value of what is a0, a1, a2, all these values we have to find out. So, that will be my interpolating polynomial. So, let us try to find this coefficient a0, a1 up to an. Now, from equation number 1, let us check what is the y at x0. So, the first initial point, this is my x0. So, at this point I want to find what is my a0 plus a1 x0 plus a2 x0 square, and in the end I will get an x0 power n. So, this is my basically this is equal to P at x0, and I know that this P at x0 is equal to y0, that is known to me. Similarly, I can apply P at x1 is equal to a0, a1 x1, a2 x1 square up to an x1 power n, and that is equal to y1. So, if I go through all these points to me that is given to us, so this is Pxn will be a0, an xn power n, and that is equal to yn. Now, to find out these values of a0, a1, a2 up to this, I can convert this equation, the system of equation, into the matrix form. Here I can write 1 x0, x0 square, x0 power n. Here I can write a0, a1, a2 up to an, that is equal to and the right hand side I will get my y0, y1, y2 up to yn. Then the next line will be 1 x1 square up to x1 power n. So on in the last I will get 1 xn square xn cube and in the last xn raised to power n. So from here I will get this value. So this is my system of equation in the form of A, or should I, because this matrix involves x, so I should write as a x A is equal to y, where this, so this is the system equation. Now this matrix, whatever the matrix we are getting, so this has a special name and this is called van der Monds matrix. Now if I want to solve this system, then let's find out that what will be the determinant of this matrix. So let's go for this one. So from here I can write the v x0 x1 up to xn. This is the determinant of this matrix, 1 x0 square up to x0n, 1 x1 square up to x1 power n, 1 xn square up to xn power n. So if you do the calculation, so this will be equal to the product of all xi minus xj, where I and j starting from 0 to n and I is not equal to j. So that is my determinant in this case. We also know that all xi are distinct. So which implies that this matrix is non-singular, which implies that the matrix van der Monds matrix is non-singular. But if these values of xi and xj are very close to each other, so in that case this matrix is nearly singular. So in that case the condition number will be very high. This method is good whenever we find that the value of xi and xj are not close to each other, they are distinct and the difference is quite good. So from here I can say that the van der Monds, this matrix is a non-singular matrix, and based on this non-singular matrix then we can solve the system to find the values of A0, A1, A2 up to An. So based on this matrix, whether it is singular or non-singular, we can find the value of this A0, A1 up to An. So this we can find out. Now the question is that once I get this matrix, this polynomial, interpolating polynomial for any k number of any n plus 1 number of points, then the question is that is this polynomial unique? Because here we are not using any of the values, we are just taking the mesh points or the nodal points whatever given to us to approximate the coefficient of the matrix or coefficient of the polynomial. So the question is that is this polynomial unique? So the answer is yes. So this polynomial is unique. So, how we can prove this one? So, let us prove. So, let us take another polynomial and we represent by p star x. So, I know that the degree of p x is less than equal to n, and also the degree of p star x is also less than equal to n, because if it is passing through n plus 1 points, so its degree cannot be more than n. So, its degree will be less than equal to n. Now, let us consider. So, consider the polynomial q x is equal to p x minus p star x. So, I choose the difference of these two polynomial as a q x. So, from here I can say that the q x is also a polynomial having degree less than equal to n. Also, q at x I is equal to p at x I minus p star x I, and this p x I will be same as p x star I. So, this will be 0 for all I, because this polynomial passing through these points, all these points, whatever the point we have. So, I is from 0, 1, 2 up to n. So, at x, any of the x I, this value and this value will be same, and then the difference will be 0. So, from here I will get the q x I is equal to this one. Now, from here, since q x is a polynomial of degree less than equal to n, which has n plus 1 distinct roots, because these all are the roots basically. So, in this case I have n plus 1 points that are the roots. So, q x is a polynomial of degree less than equal to n. So, this is the same as that my q x is, suppose I take n is equal to 2 and my q x is second order. So, that is second order. So, and I know that the second order polynomial has maximum, not maximum, the second order polynomial has 2 roots. So, but in this case it will be, it is going to have the 3 roots. So, that is not possible, which implies that this is possible if my q x itself is 0. So, it is 0 for all value of x, and from here, which implies that my p x minus p star x will be 0 for all x between x 0 to x n. Because this is true, I am taking x belongs to x 0 to x n for all value of x in the given data. So, from here I can say that my p x is equal to p star x for all value of x. I can say from here that the p x is unique. So, it is unique. The only question is that it may look like the different one, but ultimately the values are unique. So, from here I can write that the depending on its form, the polynomial is called either Lagrange interpolating polynomial or the Newton interpolating polynomial. Okay. So, these forms we know that the polynomial will be unique, but depending on the form, these polynomials has the two categories. So, first category is that either it will be of type Lagrangian interpolating polynomial or it will be a Newton interpolating polynomial. So, that we will discuss in the coming lectures, that what is the meaning of Lagrangian interpolating polynomial or Newton divided difference polynomial, because in this case we are taking the points, mesh points which are not equispaced. So, I will stop here today. So, today we have discussed about the central difference formula, that is the Stirling formula, and then we have also discussed that if the mesh points which are given to us or the data points which are given to us are not equispaced, then how we can interpolate, approximate the interpolating polynomial, and that polynomial itself is a unique polynomial. So, we will continue from this in the next lectures. So, thanks for watching, thanks very much.